What's up, guys? Today we're talking about Quicksort, the computer algorithm, and in particular, it's sorts. We'll talk about what it does. We'll give you some example code, and then we'll also talk about the time complexity of it versus other things as well. So let's jump right into it. Okay, so you can if we start off, what makes Quicksort different? What is the purpose of it? Essentially, it's just a fast way of sorting. So with other sorts, typically it's either going to be O of n or something similar, but this one, it can work with larger data sets, but also be quite fast as well. And then, in particular, it doesn't need to be checked one by one. So in traditional sorting algorithms, you'll either need to check this by this, and then this by this, and this, and this, and this. With this, we only take one item and then check all of them against that one item, and then we keep doing that over and over until we're done. So it's n log n. How the algorithm works. So yeah, like I was saying, first thing we take a giant list, or however big it is, and then we take the end of that list, and we use that as sort of a baseline, and then anything smaller than that goes over here, and anything larger goes over to here. And then when we have those two smaller nodes, we're going to go ahead and do it again. So the smaller list, we'll take the end, we'll put it in the middle, and then we'll put everything to the two sides. And you keep doing that until you have just one items all the way around. And at that point, they're all going to be the proper place in a sorted list. And so it sorts it that way. And the reason that's cool is because it's not going to do it again like bubble sort or one of those others. It's only going to get it a lot faster because it's just going to break it all out. So we can see here we have both our bubble sort and sortion and quicksort. And this shows kind of the time that it takes to perform each one, and why quicksort would be a very good option. So if it is one of the fastest ways to sort. When I was doing research on it, there did seem to be other ways that you could possibly do it that involve memory, but in particular this one, just because you're comparing it so few times that it's really easy to kind of sort it out in that fast way. And then it's n, because it's the amount that you have, times log of n, because each time you're just taking one bit, splitting in half, one bit, splitting in half. And so you don't have to do it each time. It is a lot more memory intensive though. Okay, so let's go ahead and look at a code example of this. Okay, so here we are in Writer, and I'm just going to explain this code in C# just to make it a little bit easier. So essentially we have this function sort. This is going to be the public function. This is what you call to sort your list. And then when you're importing it, you'll just have your list, and then these, it doesn't matter if you import them, but you could just have the beginning and the end of your list there if you wanted to, or -1. If you do -1 or nothing, it'll make p equal to 0. So that's the beginning of our partition, right? And if it's a list, right, that's where we'd begin on the list. And then r would equal the length of our list -1. So we're essentially partitioning it, so we're using every part of the list. Then once you have it partitioned, we check to see if we're at our base case, right, because we are using regression. And then if we are at the base case, it won't return anything, and so it'll just go through. If it's not at our base case, then we'll call the partition function. That's up here. I'll show you in just a second. And that'll show us what value in our partition is going to be what we guess against, right? So that's the middle point, essentially. So we have q, and then everything that's larger and everything that's smaller than q. And then once we have that, we can take sort, right? So the same function, put in our list, and then p, so the beginning of our list, and then q -1, right? So essentially everything, or p to 1 before q. And then that's going to be for all the smallest, and then for the largest, right, we're going to have q +1, right? Because we don't need to do q's in its right place, to r, which is the end of our list. So what does partition do, and why would that find q? So what partition does, takes in something very similar, and it makes q equal p right? So that's the beginning of our partition. And then we go through, and then U is going to be the variable we use, and we start at P, right, the beginning of our partition, and we go to 1 below R. So essentially we're using R as our variable that we find smaller or greater to. And you can see that right here. So we start with data and then in the U position, right? So essentially from this this for loop reason right there, if it's that position and we compare it to R and it's less than R, then we're going to switch U with Q. And if you remember right, Q is the beginning of the partition. And then what we're going to do with Q is add 1 to it, right? So essentially what we're doing is we're, finding the beginning, and then we slowly switch with it, if that makes sense. So Q is going to be the beginning, and then wherever we're at, right? So in this case, U, if U is less than R, then we're going to go ahead and switch it with Q and make it the beginning, and whatever was in Q will now go to U. And then we'll do that for all of them. And why that is important is because if it isn't, then it won't call any of this. So Q, right, is constantly moving to show where we're currently at in the list. And that way, if like the first time, it wouldn't change. It's still gonna stay where it is if it's smaller than our R. But if it's the third or fifth time, and we've had a couple that aren't smaller, then it will put it into the right place. And then when you've gone through all of it, that's when you get this. Because we'll have the placement of where our Q where our, right, the variable that we're checking by needs to go. And so that's where you get this part right here. So then we take, essentially what we're doing up here, right? We take Q and we switch it with R. And this way, we know where Q is, right? That's where we partitioned against. And then if we know Q, we know everything that's bigger or smaller than Q. And then once it comes back down to here, it'll go through and run that again. And we can go ahead and test this here, right? So we put in a unsorted, right? And then we check to see if it sorts it afterwards. So we'll go ahead and run that. And you can see that each of them are running currently. But this is very similar to merge sort, except for it doesn't merge back in. So you can see each one of these succeeded, which means that the algorithm is a success. Okay, and then finally I have this to show just kind of an example of how it works. We'll go ahead and start it. Okay, so quicksort. Right, you take your list, unorganized, and then you're going to find your pivot position. You take it and you center it, and then you find the smaller and the larger versions. And then you're going to do that over and over again until you have just the very basic of it. And then we'll go ahead. This case, it might look more of like a merge sort, what we just did here. In the real case, though, we would have it all be in line for each single one, right? And so I'll just let this play. But instead of having it done like a merge sort, that would be what a merge sort is having it done like that, where it splits off, but then at the very end it all merges back together. In this case, though, we only need it. We can do it in line, and that will make it faster because we don't have to go back and do it. It takes away one step. So anyway, that's a quick sort. Thanks for watching. See you guys next time.